So I will start off by giving you kind of taking one step back from DART mass spectrometry specifically and stepping back towards ambient ionization mass spectrometry. So the broader class of techniques that DART kind of fits into. So if you're not familiar with ambient ionization mass spectrometry and you're really just familiar with the chromatography-based systems, GC and LC, the difference with ambient ionization, obviously, is we're going to remove chromatography completely, and we're going to analyze the sample under ambient conditions, hence ambient ionization. We're typically analyzing the sample and desorbing the sample outside of the mass spectrometer itself, so in the atmospheric environment. And then one other thing just to kind of set the stage here too is there's a difference here between ambient ionization and atmospheric pressure ionization. So atmospheric pressure ionization is what you think of when you think of electrospray ionization or APCI or those types of things that are kind of coupled directly with an LC-MS system. It is taking place at atmospheric pressure, but you still are confining all of that ionization basically right up against the mass spectrometer. With ambient ionization, you're out in the open, typically with these setups, and you can ionize it and analyze it using a number of different ways. You'll typically hear a lot of words thrown around. If you ever read papers about this, you'll hear about that it's rapid, it's sensitive, there's minimal to no sample prep, it's easy, it's soft ionization. These are largely true, with the exception of maybe easy from time to time. But these are kind of the buzzwords that you'll hear about when you hear people discussing ambient ionization mass spectrometry in general. So ambient ionization mass spectrometry is a broad area of ionization techniques that have been developed beginning in the early 2000s with desorption electrospray ionization and then DART mass spec. Those came out almost simultaneously with one another in the early 2000s. And since then, there's been hundreds of different types of prototype and research grade ambient ionization sources that have been described in the literature. A handful of them have, like DART and DESI, made their way to actual commercially available sources that people can purchase and use on their mass spectrometers. But the vast majority still lie really in the research academic kind of sphere where they're really trying to develop ionization sources for very particular instances. You can see kind of here, this is just a word map from a recent review article on what types of terms come up with ambient ionization in general. You can see obviously DART and DESI are kind of the two biggest ones here with desorption electrospray and direct analysis in real time. Mass spectrometry imaging is another big kind of application area in the ambient ionization space. Not so much in the DART realm, but in some of the other laser-based sources that we're going to talk about in a few slides. And then there's a large range of applications that you can also kind of see on here, things from pharmaceutical analysis to biological analysis, dried blood spot analysis, some of the omics, the proteomics, lipidomics, biomarkers. Forensics obviously is a big one as well, drug analysis. There's a lot of different application areas beyond what we're going to talk about today where these types of tools lie. So there's really, if you kind of look at the entire ambient ionization space, there's four kind of major areas or four kind of major types of techniques or types of ionization sources that exist. We'll just spend one quick slide on each going through them. The first one is solid liquid extraction. So this is things like DESI, desorption electrospray ionization. And you can think of a lot of these sources as kind of a pressure washer where you're going to take a stream of solvent that's charged, and you're going to wash your sample off of your surface into your mass spectrometer. And the charged solvent will dissolve the sample and then send it off and ionize the sample and send it into the mass spectrometer. Because you're using solvents, you can add things like dopants. You can change the solvent configuration to help kind of tailor the ionization characteristics of what you want to look for. If you want to look for things in negative ionization mode versus positive ionization mode, you can change some solvents and dopants to kind of enhance those ionizations as you see fit. The downside to these types of tools is they require both solvent and gases and typically high voltage. And what you'll see in the literature is these have largely made their way into the bio space and chemical imaging space. So you'll see a lot of healthcare applications where they're doing cancer screenings or tumor analysis, some cell imaging. Those types of places are really where you're going to see these types of solid liquid extraction tools in play. The second type are plasma-based sources. So DART fits into this plasma-based ionization configuration. And what we're using here is we're using a plasma of some sort to enable ionization of that sample. Typically, we are going to combine that with some other mechanisms, such as a heating mechanism like DART uses, to get that sample desorbed into the gas phase. And then once in the gas phase, we'll ionize it using a plasma discharge. or some variation of that. The benefit of these types of sources is we don't require solvents. So if you're thinking towards field deployability and other types of applications where solvents might not be feasible within the operational constraints, this is a benefit, but you typically do still require some sort of gas to get the sample through the plasma or use the gas as the plasma to get the sample into the mass spectrometer. Wide-ranging applications here include forensics. Obviously, that's with DART. That's what we're here to talk about today. You'll see a lot of environmental analyses as well, looking at things like PFAS, and then food safety, food authenticity is another big area where these types of sources come into play. The third kind of ambient tool is laser-based tools. So similar to matrix-assisted laser desorption and ionization, we're going to use lasers to desorb your sample off of the surface. So instead of using solvents or gases, we're now going to use a laser to get that sample up off of the surface and into the gas phase for analysis. If you're in the MALDI space, you're typically going to coat that with some sort of matrix, which will help assist the ionization. So lasers are very good at desorbing your sample, not as good at ionizing. So a lot of people often include a matrix in there to help with that ionization process as well. With these approaches, obviously, since we're using lasers, we don't need solvents, we don't need gases. You do, however, have lasers involved. The reason that these are still heavily used in the analytical chemistry space is because they have superior chemical imaging. So you can control that laser spot size down quite small and do really kind of high resolution chemical imaging that you wouldn't be able to get with the liquid sources or the plasma gas-based sources. So again, you'll see these heavily used in the bio and medical spaces, really in those imaging for healthcare, for understanding cells, those types of applications. Then the final type of source that exists is what we call a hybrid source. This is where we're going to combine multiple different ambient sources, try to maximize the advantages of both of those. You'll see a lot of this with laser-based sources coupled with some sort of electrospray or DART. There's a technique called LADY, which is laser-assisted DART ionization, where we're going to use the really small fine spatial resolution of the MALDI laser, but use the DART as the ionization tool to help maximize ionization and maximize sensitivity of your analysis. Largely, these are research-grade prototypes in this hybrid space, but they are out there. There's a lot of them out in the field. You'll see a lot of hyphenated techniques in the literature, and it's typically lasers coupled with some other source or some auxiliary heating coupled with a plasma source. So we've done a lot of work actually looking at taking the heating and sample desorption component away from DART, doing that independent of the DART, and then using the DART for the ionization. So we can do thermal desorption DART, we can do infrared thermal desorption DART. There's other types of different accessories you can buy with a DART source to help increase the heating piece, which then use the DART as the ionization approach. And then with all of these, so these all are just kind of the ionization pieces that sit on the front of your mass spectrometer. And then obviously you need to then decide what type of mass spectrometer do you want to use when you're doing your different types of analyses. The good thing is most ambient sources can be mounted to almost all mass spectrometers designed for liquid chromatography. So it doesn't work for GC where you can just pull your GC off and put an ambient source on, but if you have an LC-MS system, you can pull your LC out, pull your electrospray off, and then typically you can mount whatever ambient source you want on that front of that mass spectrometer. Obviously, there's a range of different mass spectrometers that we want to be able to consider. Anything down from a single quad, if you're looking for low resolution, low cost, but you want fieldable, potentially portable, that's a potential option for you as well. If you're going after targeted screening or some sort of quantitative analysis, you're obviously going to want some sort of triple quad or QTOF type setup where you can do the MSMS and get those MSMS transitions to help with the quantitation and the targeted screening and confirmation. If you're using it in siege drug screening, like most people are, you're typically doing a non-targeted analysis. We don't know what we're looking for at the start. You want to be able to kind of screen everything simultaneously. That's why a lot of people employ time-of-flight mass spectrometers for that type of setup where we don't know what we're looking for. We still want the higher resolution because that'll help with our selectivity as opposed to a single quad. But we don't know what we're looking for, so there's no real reason to do things like MSMS unless we're doing some sort of broadband MSMS type analysis. And then there's obviously the more researchy grade systems that probably aren't as applicable in a forensic laboratory right now, but as costs drop and things become less expensive, easier to operate, things like Orbitraps, QTOFs, and ion mobility mass spectrometry may slowly make their way into the more traditional forensic space. Obviously, with all these different types of mass spectrometers, there's potential limitations. And so they really, when you're thinking about implementing these types of techniques, it's important to sit down and think about what is the application, what is the exact question you're trying to answer, and then what type of mass spectrometer is going to fit that bill the best.
First question here, Ed. So you don't need to designate an MS for DART. Do you suggest limiting the MS switching if DART and LC sharing an MS?
But yeah, that's correct. You don't need a designated system for DART. You can use the DART and the electrospray, LC electrospray on the same mass spectrometer. Some people do try to limit that. In our laboratories, I'll say we don't try to limit that. It's on a daily basis almost that we're switching out the DART and putting on the LC. We have other ambient sources as well that we'll use. So we're constantly switching things out and plugging new things in. So you don't have to necessarily be worried about that kind of swapping out. The only thing you do want to consider is is your entire analysis bulk or is your entire analysis trace? You don't want to be doing a bulk analysis on DART and then necessarily trying to go to a trace analysis on the liquid chromatography electrospray type setup. Some other things that we want to consider, obviously, the selectivity versus specificity requirements. There's an example up here on the top right where we can show two isobaric compounds. So we have AB fibonacci synthetic cannabinoid, fluoroisobutyrylfentanyl. Both have a protonated molecule at MZ369. If you're using a single quad instrument, you might not be able to differentiate these. But if you're having a high resolution system, they are separable, easily separable. I'm using a high res system. So we want that selectivity. We might want to go towards a higher resolution mass spectrometer versus a single quad where you're going to get unit mass resolution. There are some other ways to be able to differentiate these things, which we'll talk about in the coming slides, but that's one potential avenue. And then there's obviously sensitivity differences as well on the bottom right. Here's just some examples of limits of detection for a time of flight setup and then a single quad setup. And both are probably sensitive enough for siege drug analysis, but if you're looking at trace residues, if you want to also potentially use this in a toxicology setup, there are some considerations and sensitivity you might want to take into account. We've talked about targeted versus untargeted. If you're doing screening, you probably are doing an untargeted analysis. There's certainly types of mass spectrometers set up better for that than for the targeted approach and vice versa. Sensitivity requirements and the whole analytical workflow as well. And then lab versus field versus portable. There's no truly portable DART mass spec in terms of like handheld. There are some field systems. Sarah Kern will talk about the fieldable system they're using in the FDA in our 4th week. But then the majority of people so far are using this in the forensics community in a lab-based setup. And I just want one quick slide on potential thing that we want to, that our lab at least is considering into how will this apply into forensic science and siege drug screening in the future is we're completely eliminating the chromatography of LC and GC. Does it make sense to throw ion mobility separation on the front of the mass spectrometer? So there are a number of mass spectrometers nowadays where you can put an ion mobility cell on the front end. And that allows us millisecond, like very quick, rapid gas phase separation of these ions before detection. So it gives you another dimensionality of the data. It's nowhere near the resolving power of something like a GC or an LC, but it will help provide some additional level of discrimination in these setups.
Does ion mobility eliminate competitive ionization concerns?
So we haven't talked about competitive ionization yet, but we'll get there. For those of you who may not be familiar with it, the answer is we are not actually eliminating competitive ionization concerns. So unlike traditional chromatography, where your separation occurs prior to ionization and introduction of the mass spec, in ion mobility, we're going to ionize our sample first, then send it into the ion mobility cell, and then send it to the mass spectrometer. So because this is happening post-ionization, this isn't going to help address any concerns associated with competitive ionization. And then finally, we have the practical considerations, size, weight, power, cost, user experience. We want to minimize false positive identifications. Depending on what you're using this for, are false positives more acceptable than false negatives, vice versa. those are things we want to consider that might drive the actual mass spectrometry setup and workflow that you're using. What consumables are involved? There's a number of different ways you can introduce samples into the DART that involve consumables of different costs. Libraries and data sharing. So are you using existing libraries that are freely available? Are you creating your own libraries? If you have these out in the field, do you need some sort of network connectivity or reach back? These are other practical considerations as you go to implement DART in the different potential workflows that you might want to consider as well. We're going to spend a whole week on this next week, so I'm not going to go too far into this, but just wanted to let you know that the data that we're going to look at is a little bit different than what you might be used to in a chromatography setup. So with GCMS, you're going to separate on the GC column, and you're going to send a single compound into the mass spectrometer and get a spectra of just that mass, just that compound. Since we're not using chromatography with DART, we're going to see all the compounds present in the sample simultaneously. And so a single mass spectra represents all the compounds, which means it can get somewhat complicated. So this is one of the samples we've analyzed recently of a street drug where you can see there's a number of different compounds present. And then how do we go through and how do we make sense of this type of information is what we'll really focus on next week. But the good thing about DART is that, and a lot of these other ionization sources as well, is that they're soft ionization. So instead of producing fragment ions, we're typically getting intact protonated molecules, or if you're a negative mode, a deprotonated molecule. So we get characteristic information about the intact compound. We can start to get some more kind of fragment level information about the compounds that we're looking at here by using what's called in-source collision-induced dissociation, or in-source CID. You're probably very familiar with traditional MS/MS, where you're going to send something through a quad, go into a second quad, fragment a particular ion of interest, and then analyze the fragments on the third quad. So that's traditional CID, or collision-induced dissociation. With in-source CID, these are on all the LC MS systems can do this, where you have a series of plates and rings in the inlet of your mass spectrometer, and we can use voltage differences across those plates and rings to accelerate ions, increase the number of collisions, and induce fragmentation. So what we do, and what a lot of labs do, is they cycle through kind of a series of these different voltage differences to get intact molecule information as well as some fragment ion information, as you can see here. So on the right-hand side, we have 3 mass spectra that we collected simultaneously from the same compound. So you can see the intact molecule, the protonated molecule on the top right, or on the top one. And as we increase the voltage, so we go from plus 30 voltage difference to 60 to 90, you can see we induce fragmentation. So we're introducing fragmentation along that mechanism as well, which can help kind of determine which compound or compounds might be present. The difficulty here, however, is that since we don't have that chromatography and we don't have MS/MS, we're fragmenting everything simultaneously. So again, it can make that data, those resulting mass spectra, look quite complicated. So this is just a single compound, but if you can imagine the slide before, we had 7 different compounds present, you're gonna have a big difference there as well. One of the last few concepts I just wanted to highlight, which the question was brought up earlier about competitive ionization. Basically what competitive ionization is that ionization suppression due to the presence of a more easily ionized compound. So think about a mixture. If you have a neat compound and you analyze that with DART, you're obviously going to get a signal for the protonated molecule for that compound. If that compound is a major component in the mixture, you're going to get, and you have a secondary component, you'll get a signature for each. Depending on the ionization affinities of these 2 different compounds is going to drive which one you're going to see more or less signal of, in addition to concentration. So it's not purely a concentration-based response you're getting when you get into the mixture space. What might happen is, let's say these blue molecules are the more easily ionized. If you have them in excess, you might actually completely miss the signal for the red compound because the blue is going to consume all the available charge, and you're not going to be able to see the signature of the red when it's present as a minor component in that mixture. So we've done a lot of studies in our lab to kind of look and see where these types of where this competitive ionization effect might occur. Obviously, in a siege drug screening environment, we don't want to be missing drugs in our screening approach. We want to be able to make sure we can identify them pretty easily. So here's just another example, an actual real-world example, looking at different levels of methamphetamine versus caffeine. You can see when we have pure methamphetamine, we get a nice strong signal for it in the red box here. If we put an equimass mixture of methamphetamine and caffeine, you can see you get a much higher signature for the caffeine relative to the methamphetamine. So even though they're at roughly the same concentration, you don't get an equal response because the caffeine is going to be a more easily ionized compound. And then when you go into the excess of caffeine, you now have an excess response of the caffeine, and you have a much lower response of the methamphetamine. We have a question that came in that's, does competitive ionization impact being able to do quant? Potentially. It's going to depend on the types of internal standards that you're using to do quantitative analysis. So we're going to talk about that more on week 5, but if you're using kind of deuterated internal standards or internal standards that are relatively similar to the compound that you are interested in quanting, you should be able to get a relatively high level quantitative value. If you're kind of using unrelated, chemically unrelated internal standards or no internal standard, then if you're looking at mixture analysis and trying to do quant in there, that might become pretty difficult. One last slide just to show, kind of bring this point home. Again, we've done other studies as well with fentanyl, heroin. The good thing is we've looked at fentanyl. We know that's typically a low-level component of street drugs. That one does not seem to be affected by competitive ionization. Heroin, on the other hand, does actually get impacted by competitive ionization. So if you have kind of a non-traditional drug mixture where you have a lot of fentanyl and a little bit of heroin, you might actually not be able to detect the heroin because the fentanyl is going to consume all that charge. There are some other kind of cutting agents. So if you have really high levels of procaine, benzocaine, or lidocaine, you can see some competitive ionization effects in there as well, especially with heroin and a little bit with some of the other drugs. So just to recap, this was just to give you guys kind of a broad overview of what ambient ionization is. It's a broad suite of different sources that enable rapid analysis of samples. There are those 4 major classes we talked about: solid liquid extraction, which is basically the pressure washer approach; plasma, which is what DART is like; laser-based systems; and then hybrid, which is where we're going to combine multiple of these other 3 sources to get the best of both worlds from multiple different sources. We can mount these to pretty much any LCMS system. We cannot mount them to GCMS systems. We do get complicated mass spectra, which will be the focus of next week's discussion of how we actually deal with that. And then a few of the things important concepts we want to make sure we drive across are competitive ionization and then in-source CID. You'll hear a lot about that in the following weeks with people using multiple different fragmentation spectra to kind of help enhance the confidence in their identification. So that's all I have for right now. If you guys have additional questions, we'll certainly be able to answer all of them in the Q&A section at the end of the day. But with that, I'm going to throw it over to Dr. Chip Cody, who's going to give you narrowed in onto DART mass spec exactly and give you kind of the fundamentals of what DART is, how it works. So Chip, the floor is yours.
Okay, thanks, Ed. I'll go ahead and share my screen here. Great. Okay, I'm going to try to give you a real overview of DART, including just about everything, but might mention this is kind of the 20th anniversary of DART. First spectra I could find are actually in January 2003, and it's been an interesting ride for the past 20 years as we learned new techniques. I won't spend a lot of time on the history, but I will mention DART actually predated DESI, although DESI was the first published application. And you wouldn't guess this, but the first published forensic application was actually for question documents from Ames Lab, where they looked at identifying ballpoint pen inks. I think some of the real milestones in forensic application, of course, were the drug screening validation by the Virginia DFS and development of the NIST DART forensic database. A number of other things have happened over the past few years, but those were some of the real milestones for forensic DART. I'm going to show you just 1 or 2 applications for those of you who haven't seen it. Doing this on our Joel Akutov DART system, where the DART was born. The video goes a little bit longer. I'm only going to show 1 or 2 applications because of time. But let's start this thing. First application, I'm just going to look at the caffeine in my coffee. I'm just dipping the sealed end of a melting point tube in my coffee, and I'm going to wave that in front of the DART. So you'll see in a second as the video continues, the blue DART source on the left, the gas is coming out of that white cylinder, and the gas is directed into the sampling orifice of the mass spectrometer. And the caffeine pops up in real time. Depending on temperature in the coffee, you'll see lipids in the coffee cream. You'll see some other things that are present in the coffee. Here's a basil leaf. We can actually detect drugs both in and on plant material. So there's a restaurant story behind the basil leaf, but you'll see in a second. This was grocery store basil, mostly eugenol for the flavor component, but you can see the spectrum there. And I think I'll show you one more. We're seeing plant sterols too there. I'll show you one more example. This is an elastic band. It's not really rubber, it's silicone, but you can see we can put objects into the DART gas stream. The video is going to go on after that to do gunpowder particles and motor oil and things like that, and the powdered drug. But I'm going to go ahead and stop it here after you see this example because we don't have a lot of time to dwell on this. But it does show you how fast the DART is. You can put an object in the gas stream and get a spectrum very quickly. Okay, so I'm going to actually give the talk backwards. Before I explain how DART works, I want to think about what information we're getting from DART. Ed talked about that to some extent. I'm going to take it a little further and talk about what we get from the high-resolution time-of-flight system. To begin with, for drug screening, DART is a SWIG drug category A method. So for confirmation, you'll need at least one other method if you're following the SWIG drug guidelines. But because DART is a form of mass spectrometry, that makes it a Class A technique. Now, the limitations from the SWIG drug documents, point out that mass spec can't discriminate enantiomers, and it can't really be used to identify salt forms, although we've had some ideas about that. Some fragmentation can occur. DART is a softer ionization method, but I'll show you a couple of examples where fragmentation occurs. And some of the things that we think of for GCMS are not necessarily true for DART. We can distinguish between psilocin and psilocybin, for example, and we can detect barbiturates. But there are a couple of other gotchas that we'll have to worry about later. The information in particular, though, we're going to get elemental compositions from the DART data using both the accurate masses and the isotope data. For fragmentation, of course, is required for distinguishing isomers. For some applications, for example, the Fish and Wildlife forensic application, where identifying illegally traded timber from endangered species, we look at mixture patterns, and some of the trace evidence applications also look at patterns of formulations or materials. Quantitation is possible if you can calibrate a response. You have to make sure you can demonstrate a validated method, and that includes taking into account matrix effects and internal standards. But the internal standards are necessary to correct for gas turbulence, which will affect the absolute sensitivity. DART generally gives you simple spectra, as Ed showed earlier. Here's an example of sunscreens and a sunscreen applied to a fingertip. Essentially, we're getting one isotope cluster per compound. And we're getting molecular formulas and fragment compositions. So standard condition gives you mostly molecular species, but we can also get elemental compositions. We're measuring masses to errors in the third or fourth decimal place. And just for perspective, the mass of an electron is 5 times 10 to the minus fourth mass units. But the isotope ratios are also really important. So I'll show you an example of that in just a moment. Once we have an elemental composition, we can search online databases for candidate compounds that might have the same composition. And that's going to give you a list of isomers. You can see if we just had the elemental composition for fentanyl, of course, there are an awful lot of isomers that aren't going to be distinguished by the elemental composition alone. For data analysis, this is a little bit of the boring part, but if we want to talk about data analysis next week, I'd like you to know something about what the terms are. So bear with me for just a minute. First of all, resolving power is the ability to separate two closely spaced peaks. And the traditional definition is the mass that you're trying to measure divided by the difference in masses that can be separated. So this is really how well we can separate closely spaced peaks. It's relevant to the time of flight discussions. It's not really relevant to the quadrupole section. But here are two examples for C36 hydrocarbon. You can see the difference on the left between a resolving power of 500 and that of 5,000. the peaks are narrower, and you can see differences between closely spaced things. The resolving power definition varies, but most of the applications we talk about use the half height definition. In other words, how wide is your peak at the half height? That's what's used to calculate the resolving power. Here's why high resolution can be important. This is heroin in a urine sample at 30 parts per billion. This is done with solid phase microextraction followed by DART. But you can see, if you're just looking at the 370 peak, there's an interference at 370.3094, and that's a background interference in the urine. If you don't have the high resolving power, you aren't going to distinguish between these two peaks. When we talk about mass accuracy, most of the time we'll just be talking about millimass units or 0.001 mass units. All of my talks, that's what I'm going to use. Some of the literature uses parts per million, where it's, the difference in mass between calculated and measured divided by the mass times 10 to the 6. I really do not like that term. I recommend that you don't use it unless you have to, because it's a mass-dependent term. It lets you get away with poor mass accuracy at high mass and requires high mass accuracy at low mass where you really don't need it. In the software, again, later you'll see, next week especially, we'll see talked about even and odd electron ions. In most cases, DART produces even electron ions. In other words, the protonated molecule, M plus H plus or M minus H minus. The software can sort out the difference between the two compositions, and this is actually just a parameter you can use to limit possible elemental compositions when you try to figure out what something is. You also see unsaturation and double bond equivalence. This is a calculated number that's calculated from the elemental compositions. It's just a rough guideline about the number of rings and double bonds, or degrees of unsaturation in a structure. And the only reason that's important is that if you calculate this from the elements and their valences, you'll get a number that can distinguish between even and odd electron ions. I won't spend a lot of time on this right now, but I'll show you an example in just a minute. So here's an example. This is where we take a fentanyl spectrum. And you might recognize those masses from Ed's example earlier, but when we do an elemental composition calculation to find a complete unknown, all of these things are parameters that you can specify to try to limit the number of elemental compositions that you're going to get. Now, I'm going to stop for a second and share a different part of my screen. This is just an example of an elemental composition calculation from a DART spectrum. So suppose you have 3 peaks and they're complete unknowns there. You can take the exact mass data and the isotope data and try to figure out what, for example, the 316 peak is. So if I choose the 316 peak, I'll give it a list of elements that might be present, calculate the possible elemental compositions, and we're going to get a list of possibilities, but we can use the isotope data to sort those out, and it turns out the correct composition is C18H22NO4. And if you look at the NIST database, there are 114 entries that, no, I'm sorry. Let's do this. That's still the correct composition, but why am I missing this? Oh, I know why. Oh boy, okay, well, this example isn't going to work very well. But those are the correct compositions. In fact, if we search for these things, you can see the software can identify which drugs are present. We've got tetracaine, which is an added internal standard, and oxycodone, which is the drug in question. And this is identified by the elemental composition and the isotope data. We can talk a little bit more about that next week, but let's go back to sharing the screen.
Hey, Chip, real quick, a question came in.
Sure.
Maybe you'll cover this later on, but can you use other gases with DART? Always?
Yes, that's going to be part of the talk.
Well?
Yeah, that's part of the rest of the talk. Elemental compositions, of course, aren't enough. You need to be able to distinguish between isomers. My favorite example is the fact that morphine and piperine and black pepper both have the same elemental composition. So if we're going to distinguish between those and not bust somebody for carrying around a packet of pepper, we need to have additional information. And that's where we use the in-source CID that Ed talked about earlier. Here's again, you can see the fragment spectrum from fentanyl spectrum. If we look at the fragment compositions, they also give us structure clues that might help us to try to identify an unknown. We've applied this to NPSs sometimes to try to get some information about the substructures that are present. We can also do pattern matching. This is more a trace analysis example, but if you do pyrolysis with DART, you can get fragment patterns from things like large polymers that can be searched against databases. That's also useful for formulations or excipients or contaminants. We've used this to look at the sources of drugs, for example, impurity profiling, or counterfeit drugs and trying to identify the source. One of the major applications for DART that's not involving drug forensics is identifying wood from endangered species. And Fish and Wildlife Forensic Lab has developed a database of angiosperms from endangered species that can be used to identify this. In this case, we're just matching the DART mass spectrum pattern against the database. There's a little more to that than we have time for today, but that's an important application. We can also do things like classification, identify differences between different species. We've done this with insect species, with plant species, even formulations like the volatiles from bourbon and Scotch and rye whiskeys. You can also do thermal desorption and pyrolysis. Ed has one approach for doing this. There's also another little stage that can be used to measure particles or fibers or powders by controlling the heating. And as you can see, different components desorb at different times. So we don't actually have chromatography here, but we do have some sort of rough thermal separation that can be useful. What we can't do by DART alone is to separate isomers in complex mixtures. You really need chromatography for that. DART has been combined with both GC and LC, but it isn't really sold or operated that way routinely. We can't analyze permanent gases because they're present in the air. And DART isn't very good for very small hydrocarbons. You can get a spectrum from hexane and things like that, but it isn't really a useful way to do that. DART isn't good for proteins or peptides, atomic elements or metals, larger highly polar compounds, and nothing other than MALDI really can give molecular weight distributions for large polymers. But there are other ways to do these things, and I can talk about those a little later if we have time. But as it is, I'm just going to give you an overview of some of the other kinds of ionization methods that we've done for things that DART isn't very good for. So to a large extent, with our system and swapping out some of the different ambient ionization sources, we have a pretty good probability of getting information for almost anything. There are a lot of publications here. You'll have the PDF of this talk available later, so you can look these up. But these are some of the benchmark papers, especially relevant to drug chemistry. And Ed and group wrote a forensic application review just recently. I think would be quite helpful. Aside from drug chemistry, these are some of the other applications I've mentioned: question documents, chemical agents, sexual assault investigations, explosives, trace evidence, forensic entomology, psychotropic plants, and even some applications to toxicology. If people are interested in that, they can contact me for references to some of the work done by some of these groups. Now, with all of that, let me finally get around to talking about how DART works. DART is actually pretty simple. We originally designed this to be used with ion mobility, although it hasn't been used with that very much. But the DART's basically just a glow discharge carried out in a tube with gas blowing through it. In the glow discharge, all sorts of unstable energetic species exist, but they rapidly collapse to give you excited state atoms or molecules, which are blown out of the DART source onto the sample. And the long-lived excited states are called metastables. For example, electronically excited helium atoms that have a long lifetime. The sample's blown out of the tube and samples are ionized in the sample gap. And if you look at this in a schematic form, it's basically a needle electrode and a counter electrode with holes in it. And then a gas heater tube that blows the gas out of the exit. There's an exit electrode that's biased positive or negative, determining whether you're looking at positive or negative ions. and an insulator so that you don't expose your finger to a couple of 100 volts. Then the sample is deposited in the sample gap, and the ions formed from the sample are blown like leaves in a stream into the opening of the mass spectrometer vacuum system. The only thing you can't do is stick the sample directly in front of the hole into the vacuum system and block the gas flow. But usually the sample, the gas is not interrupted by the sample. First step of DART ionization is called penning ionization. We have excited state neutral atoms with a lot of energy in them, and they'll transfer their energy to a sample to produce a positive ion and electron. Most common gas is helium, and that's because helium has about 20 electron volts worth of internal energy. That's a ton of energy. Most organic molecules ionize at about 8 to 12 electron volts. So this step is the only thing really that distinguishes DART from forms of atmospheric pressure chemical ionization or atmospheric pressure photoionization. After this step, then it's mostly ion molecule reactions. So the first step for positive ion DART is generally just that the helium ionizes water, and the water clusters and forms protonated water clusters. So you've basically got a kind of a gas phase acid that will transfer a proton to a suitable sample. A suitable sample is something with a heteroatom, a site of unsaturation, someplace where the sample will take a proton. If you look at the DART background on the ecutoph, you can see mostly we form protonated water dimer and a little bit of trimer, just a little bit of ammonium, a little bit of protonated water, and maybe a trace of oxygen in the background. But this is typically what's reacting with your sample to ionize it. Negative ion mode is less useful for drug screening, but it's used for other things. Most of the time, you'll see that the electron produced in that first step will attach to oxygen, and oxygen will pull a proton off of an acidic sample. So in simplest form, I'm going to ignore that, but in simplest form, in positive ion mode, you get M plus H, and in negative ion mode, you get M minus H, just like this. Now, other things can happen. And Ed talked about competitive ionization earlier. Li Guosong and John Bartmus and Kelsey Cook and company called this the transient microenvironment concept. But in simple terms, it really just means that the DART atoms ionize something. That something could be atmospheric gases or something you deliberately add to the gas stream, or it could be one of the components in your mixture. And whatever that thing that gets ionized first is, ionizes with the other components in the sample to produce what you see. A really nice example of that is codeine and acetaminophen. The Virginia DFS group noticed that if you just ionize codeine by DART, you'll get M plus H at mass 300, but you also get M plus H minus water. And that's because there's a big energy difference between the water clusters produced by DART and the codeine itself. But if you look at Tylenol and codeine tablet, you get very much more of the M plus H from the codeine and a whole lot less of the water loss. And that's because the first thing that's ionized in a codeine acetaminophen tablet is actually the acetaminophen, which then transfers its protein to the codeine. The moral of this story is that matrix effects or competitive ionization can either work in your favor or work against you, and you'd have to keep in mind that things can happen when you have mixtures. In most cases, this isn't really a problem for DART, but it can affect if you have a trace component in the presence of a larger interference that's going to steal all the protons. I'll just leave this with you for follow-up, but we know what kinds of molecules and what kind of functional groups tend to work with different forms of DART. In most cases for the drug analysis, we're going to find proton transfer. So we'll form M plus H and we'll operate everything in positive ion mode. There are some artifacts you can see. You have to beware when you look at soft ionization methods. This is a DART mass spectrum of methcathinone, and there's an extra peak right here at 327. I wonder if any of you can guess what that is. I know some of you will know right away. It's actually a proton-bound dimer. You have some extra neutrals in the cloud around the protonated methcathinone, and they'll form a cluster ion of 2 methcathinone molecules plus a proton. You can also get mixed dimers if you have mixtures. So sometimes you'll see a series of recognizable drug peaks out here, and you'll see another series of cluster ions in the dark mass spectrum. So don't be surprised if you find some unexpected things at the high mass region. What about temperature? Well, temperature is a parameter. The dark gas temperature is a variable. Typically, it's about 50 degrees C with the heater off, up to about 500 degrees. And the hot gas is going to help to desorb low volatility materials, but there's actually some evidence that dark desorption is more than just thermal desorption. Heat can increase fragmentation. So for materials analysis, we'll often use a very high temperature to do in situ pyrolysis. But when you look at the DART controls, keep in mind that the actual gas temperature is lower than your setting. If I set the DART heater to 350 degrees, the actual DART gas temperature is going to be cooler than that because the gas starts to cool down as soon as it exits the DART. So for a very rough practical guide, if you're looking at energetic materials like explosives, you want to set the DART heater to 200 degrees or less. That's not necessarily because they're going to detonate, because they won't unless there's an oxidizer present, but because they'll fragment. Typically, I run the drug analysis around 300 to 350 degrees. If you have a specific analysis, you can vary the temperature and find out what works best. And for polymers and materials, I tend to use high temperatures. Just briefly, I'll talk about what's in our mass spectrometer, because the DART was born on the Akutov system, which was originally an LCMS system. It looks complicated, but there are really only 3 major parameters. One is the collision energy, which is the potential difference between these 2 skimmers. The other is just the ion guide, which is the lowest mass we're going to detect. And the third is just the detector voltage. So the important part here is the potential difference. When you look at the NIST DART forensic database, you'll see that there's for each drug in the database, there are 3 or 4 potential differences, 20, 30, 60, or 90 volts. Those are the collision energies for the in-source fragmentation. And we can actually program the software to switch those at a rate up to 10 hertz. Typically, I'll run 5 different voltages per second, because a typical DART analysis is the signal is going to persist for several seconds. If you are not using the DART on the Joule system, you'll also have what's called the vapor interface that IonSense developed. And that's because most other mass spectrometers can't pump helium directly. It also kind of provides a universal interface for DART on other systems. It does improve reproducibility a bit, but it has some other characteristics that you should be aware of. Here's a picture of the vapor interface on our system and the system without it. I can compare directly by running the system both ways on the same mass spectrometer. One thing is that competitive ionization is going to play a bigger role if the vapor interface is present. That may be less of a problem for drug molecules unless you have complex mixtures, but I can see if the vapor interface isn't present, I can actually see the reagent ions, the water clusters in the DART spectrum. I can't see that if I put the vapor on, because these things are very reactive. They're going to react away as they're being transported down the ceramic tube. The vapor will also decrease the signal for nonpolar compounds. Here's epitestosterone and quinine. And if I put the vapor on, measure the same sample, the epitestosterone is diminished. And actually, the total signal is about half. The trace of methyl stearate that's present is actually gone. That's because the quinine is polar. It likes the protons. The other things are going to lose their protons to the quinine as they transport down the gas stream. You also see some other differences if you work with the vapor interface. Ammonium adducts tend to be favored over proton adducts for molecules that don't have a basic site. Now, the question is asked about what are the gases we can use. Helium is by far the cleanest and most predictable of the DART gases. If you could use neon, it would give you almost exactly the same spectra as helium, but at the moment, neon is more expensive than helium. That's because all three of those have excited states that are enough to ionize water and oxygen. If you move to argon, then you find that these cannot ionize water and oxygen, and so you have to add something to the dark gas stream that these gases can ionize, and then let those react with your sample. I'll show you a brief example of that later, but the other gas that's commonly used is nitrogen. Nitrogen actually doesn't have a large metastable energy, but it does react to ionize your samples. I'll talk about it in just a minute. The spectra can be a little more complicated with nitrogen, and nitrogen won't heat the samples as much as helium, but it can work. If you do argon DART, you don't ionize the water, so you don't get those water reactions I talked about earlier. But you can add something to your DART gas stream. For example, here's we've added chlorobenzene to the DART gas stream. That'll charge exchange to give you molecular ions for things like beta carotene. There's only one really important forensic application for that, and that is distinguishing between THC and CBD. We may have time to talk about that more later, but if you just do helium DART, THC and CBD give you exactly the same fragment spectrum. But if you do argon DART, then you form the molecular ions which fragment differently. I listed some articles from Ravi Musa's group because they've been very prolific on DART and drug chemistry. You won't be able to read those, but if you get the PDF file or if you look at Ravi's publication list, you can see all of these here. Michelle Peace's group has quite a number on vaping and e-cigarettes and some other toxicology examples. And go back to the nitrogen example. Let me just show you what happens with nitrogen. This is chlorpromazine, which is kind of a thermometer molecule for oxidation. If you do helium DART, chlorpromazine gives you mostly M plus H. But if you just do nitrogen DART without any other tricks, you will get a lot of oxidation. I'm not really quite sure what the mechanism is here, but I think nitrogen is forming nitric oxide, which is really reactive. Now, this is okay if you're screening for chlorpromazine, but if it's an unknown, it could be confusing. One way you can reduce the oxidation is just use an exit insulator with a small hole. What I think is happening is that some oxygen gets back into the DART close to where the exit electrode is, and that's what's forming the nitric oxide. But if you make the hole small, less oxygen get back into the DART, and you can reduce the oxidation. Here's an example. Here are the reaction ions for helium, mostly water, like you saw earlier. But with nitrogen, you've got nitric oxide being formed, and that's going to oxidize your sample. And that's confusing. But if you use a small hole, you get a little more water dimer, you get less nitric oxide, and you see more M plus H, and the spectrum is clearer. Now, you don't, there's always something you trade when you get, you can't get something for nothing. What you lose here is that you have a smaller gas stream. It's a little harder to heat the sample, and it's also harder to find out where the gas stream is coming out of the hull. But with that said, this should make nitrogen DART a little bit easier. The spectra, most cases, the fragment spectra can be searched against the database, but we get smaller hit factors compared to using helium for drug screening. If helium cost is a factor, you can actually use DART gas pulsing, which is offered by the DART as the DART jump shot from IonSense. You can see here we're pulsing the gas on. That'll save quite a bit of sample, and if you're using auto sampler, then you get nice discrete spectra for each of the different samples. I'm just going to really zoom through the rest of this. There are some examples for trace analysis using a thermal desorption and pyrolysis stage. I won't explain that right now, but if there's time later, we can talk about it. I'll give you temperature profiles. Quantitation, again, gas turbulence is the main factor affecting signal reproducibility, but you need to use reproducible sampling methods and use an internal standard. And you'll have to check to make sure your internal standards have similar ionization behavior and similar desorption behavior to the samples that you want to quantitate. So isotope labeled standards are always ideal, but homologs, for example, promazine and chlorpromazine, can often work. I will mention that nobody's software really does DART quant very efficiently, except for this software from SpectraWorks in England. Their Analyzer Pro XT software actually has a DART and ambient ionization module that lets you work with kinds of samples you see from the gas pulsing earlier. Otherwise, you really have to just export peak areas and put them into Excel and work with them, which is tedious. Here are 3 random quantitative DART applications. Here's one from Ed's lab where they quantitated ethanol in alcoholic beverages. I've actually used that to check the alcohol concentration in my home brew. Andy Grange, very early on, showed drugs on surfaces and showed that they could certify decontamination of clandestine labs by swabbing the surfaces to see what's left. And Robbie Musa's group with Megan, who'll be talking later in this workshop, is actually quantitating cannabinoids and edibles with DART. So there are some very useful applications for quantitative DART analysis. I won't mention much here, but there are other tricks you can do with DART for nonpolar compounds, hydrocarbons, and alcohols. You can actually form oxygen adducts by using the DART to generate O2 minus and letting it attach to the molecules. This just shows you the difference between a motor oil spectrum and positive ion DART. We see all the additives, and the negative ion spectrum, we actually see the base oil. That's a lot over a short period of time, but I wanted to try to get it all in the time and leave some time for questions. So I'll go ahead and pause there and let everybody take back over for the question and answer session.
Awesome. Thanks so much, Chip. Yeah, if anybody has questions, feel free to put them in the chat pod or use the raise hand feature. We did have a question come in during a talk that I didn't want to answer at that point because I was not probably the best time for it, but how is in-source CID different from MSMS?
The difference is that a true MSMS, you have a mass spectrometer, like a triple quadrupole system where the first mass spectrometer isolates a specific M over Z, and you fragment only that M over Z. In-source CID, everything is fragmented, and we'll talk about the data analysis for that more next week. If you're doing LC with in-source fragmentation, then you have one component at a time. That's often very clean. But for DART, we're ionizing everything, and they all get fragmented, and you get a superimposition of the fragment spectra for the different components.
Thanks. Let's see. I'm waiting for other people. Just in case people don't know, you mentioned glow discharge several times. Can you just provide a little background on what that is in case they're unfamiliar?
Sure. Glow discharge happens when you have a high voltage and in the presence of a gas. If you actually turn the DART on in a dark room and look down the bore, you can actually see a pale purple glow. The glow discharge contains all kinds of excited species. It contains helium ions. It contains electrons, xmers, dimers. I mean, it's a really energetic plasma. The glow discharge is a little bit different from a corona discharge, where the glow actually it's the voltages and geometries are slightly different. The corona discharge is using APCI sources, and if you're looking in a dark room, you just see a little faint glow right around the tip of the needle. The glow discharge is a little more aggressive. Glow discharges are used in other technologies for elemental analysis, for example. But in the DART case, we're looking at what's called the flowing afterglow, which is what happens after the gas exits the glow discharge region. And the electrons and the positive ions recombine and leave you with excited states.
Thank you. Anybody has questions, feel free to raise your hand or turn your video and go off mute or send something in the question and answer.
I sailed through an awful lot of that material really fast in the second half of the talk, so please feel free to ask questions. And a lot for the drug screening application, we're going to go back to much simpler conditions. I mean, so a lot of the extra stuff I talked at the end is not relevant. That's more relevant for other forensic applications.
It's important to highlight that because I think for some labs, it might make sense to demonstrate cross usability of something that's going to require a high capital investment. You said most drugs are negative, or I'm sorry, are in positive mode. In your expertise, have you seen anything that's better off in negative mode?
GHB, for example, the aspirin, acidic compounds, things like that. All of those will form positive ions. I mean, even things like the barbiturates, which are traditionally negative ion compounds. But if you have an acidic or phenolic compound, those things tend to be better in negative mode. I think there was a challenge distinguishing between GHB and GBL, but that was in some of the first papers where the FBI lab looked at GHB in urine.
And we've also seen a lot of other, your synthetic cannabinoids, your benzos, they'll work well in both modes. Positive.
You've had things like sulfates too. Those things are certainly going to work better in negative ion mode. Another thing that's sometimes useful is just seeing what the counter ion is for a salt form. You should be able to just detect some of Cl minus or I minus in particular, sulfates, that kind of thing. Oh, and explosives too. Most of the explosives are going to work best in negative ion mode, except for TATP and acetone, peroxide explosives. For chlorites, you talked about that with thermal desorption. That really, those are definitely much better in negative ion mode.
We do have a question come in. How much lag time does it take to do the switching between positive and negative ionization modes? Would it be practical to implement in different methods?
On the Akutov system, it's really based on the mass spectrometer. I mean, switching the DART ionization is instantaneous. On the Akutov, we actually deliberately ramp the voltage down over maybe 15 or 20 seconds and ramp it back up again so that we're not shocking the detector by switching between plus or minus 2000 volts. But it's very quick otherwise. I mean, it's really just a matter of loading the parameters and letting the mass spectrometer switch polarities. So we often do both quite often.
Another question, what is the time frame from, okay.
Go ahead. I was going to say, if you have complete unknowns, it's always a good idea to analyze it both ways.
Definitely. That's what, I mean, if we have an unknown NPS or something, we'll analyze the positive and negative just to see what we can see. And we'll do the counter ion as well. We'll do dissolve it in water and do a counter ion. Another question, what is the time frame from the sample in the stream to the analyzed spectrum?
That's actually a better question for next week. I mean, it only takes a few seconds to measure the sample. And depending on how you want to handle high res or low res data, that's pretty quick. I mean, the quickest thing is if I just right click and do library search for 90 volt spectrum and search it against the NIST DART forensic database. But if you want to do a little more detailed analysis, we'll either with Mass Mountaineer or the DART data interpretation tool we'll talk about next week, you'll want to use the software to compare the spectra measured at different voltages. So it really doesn't take very long, honestly, just a few minutes, and some of that can be batch processed.
Yep, I'd agree. On our end, I think, if we're using the DIT, it's probably within 90 seconds, start to finish, we can analyze and report. Since you're not asking any questions, I don't know if you wanted to dive into the THC CBD a little more, or one of the things people might be interested in.
I could back up, I guess, or I can just explain what happens when you protonate. You add a proton to THC or CBD, they cyclize to form an ion that has exactly the same structure. And then when you fragment that within source CID, the spectra are indistinguishable. There are different ways you can approach that. One is derivatization. Glenn Jackson's group showed that just by doing, you can do in situ derivatization with DART. I didn't mention that, but for example, not getting off track too much, but if you want to detect psilocybin, you can do in-source silylation just by putting a drop of MSTFA on the sample and sticking it in the DART gas stream, and the reaction is instantaneous. The same thing goes for THC and CBD, because you've got a single hydroxyl or two hydroxyls that can distinguish. But the problem there is just that the protonation changes this ion structure to be the same, and they fragment differently. I mean, they fragment identically. You'll see slight differences in the negative ion spectra, but But if you do argon dart with chlorobenzene, chlorobenzene doesn't put a proton on the sample, it just forms a molecular ion. And the molecular ions for those two fragment differently. There's another approach too that Rafi Musa's group has taken. It doesn't, it's not a validated method for hemp and marijuana. Just, it's not the 0.3% THC thing, but she's looked at the fingerprint patterns of cannabinoids in the two and can distinguish between the two just based on the distributions of the different cannabinoids, and that's been published. And Megan might be able to talk about that. I think she might have been involved in some of that work.
We'll make sure to bring that back up. Her approach, her talk. And a question I get often, which people might have, is there auto sampling capabilities with DART, or is it all manual?
Well, there are auto sampling capabilities. I mean, IonSense provides. Oh, I showed one with the pulse gas. That's where you spot samples on a screen, and you scan up to 12 samples on mesh in front of the DART. We've also deposited samples on melting point tubes and used that same sort of method. There are 96 well plate variations. People have used robotics with DART too. Because it's an open air source, there are an awful lot of possibilities, but the easiest ones are the ones that IonSense provides with the linear rail. I do like using auto samplers for quantitation because it's much more reproducible. And if you want to make sure that you're really seeing differences between things, you want to keep that sampling as uniform as possible. And the mesh is using what's called transmission DART. Facundo Fernandez's group showed that early when they were looking at anti-malarials on insect repellents on mosquito netting, and they found that if you blow the sample through something, it's much more reproducible than wiggling an irregular sample in a dark gas stream.
I definitely agree. We did have another question come in. Have you been experiencing any identification issues of analytes like general unknowns in trying to account for mass defects without knowing the elemental composition?
Not so much, and partly because the isotope data is so important. If I were just using exact mass only, I'd actually have a hard time distinguishing the same things. I wrote an article for Joel blog years ago about exact mass and elemental compositions, and I left with the conclusion that chlorpromazine was really hard because you've got chlorine, sulfur, phosphorus, carbon, hydrogen, nitrogen, and oxygen all in one molecule, and even with exact masses you still end up with a few possible compositions that were indistinguishable. But it turns out with the isotope matching from the time of flight has really good isotope accuracy, then you actually can identify the correct composition. But we also take advantage of searching the databases to see what molecules have those formulas. It's a little bit like what Jim Little called known unknowns. If a molecule exists with that formula, it's probably something you should take more seriously than something that isn't known in the literature in PubChem or ChemSpider or CompTox or something like that. And a silly thing, but if a candidate molecule has more synonyms and is in more databases, it's more likely to be an important molecule. Remember, elemental compositions alone are just the first step in the identification, and then we have to look at fragment data and other information to try to identify. I mean, some molecules we don't know from any of the DART data at all. We don't know what some of the wood molecules are. Some of them are known. Dalbergen is in Brazilian rosewood. But some of the other things, we just know that they're flavones and we don't know what they are at all.
Yep.
That was kind of a long-winded answer to a shorter question. I hope that helps.
No, I think that was good. Yeah, I think that was good. Like you do, we look at the elemental composition, we look at the isotopes, we look at the DART fragments. Then if it's unknown, we'll also run it on GC or LC, and we'll look at that information, and we'll do mass spectral similarity or hybrid search in that space as well. Try to get as much information as we can out of it.
Yeah, complementary information is helpful too. If you see both M plus H and M plus ammonium, or if you see M minus H and chloride adducts in negative mode, or sometimes if you're lucky, you can see M plus H in positive and M minus H in negative. All that information is helpful.
I'm not seeing any other questions. You have any final thoughts, Chip?
No, I hope this was helpful for everybody. I recognize some familiar names in the attendees there. So anybody feel free to contact me privately if, or by email or whatever if you have questions. I'd be happy to follow up. We'll talk more about data analysis next week.
And speaking of contact information, if you need Chip's contact or my contact, they're up here and ready for you. They'll also be on the slides in the Moodle area.